Hi everyone. In this video we will see the Clarke's transformation for FOC control. As you know that FOC, which is also known as the field oriented control, is being widely used for the control of the AC motor, specifically for PMSM and the induction motor. And both these two motors are very popular in the electric vehicle. So through this video we will see the derivation. We will also see the how three-phase values can be converted on a to orthogonal component, and we'll also see that how subsequent to the Clarke's transformation, how the Parkes transformation can be done. So let's begin. So in the FOC theory, we know that if we consider the DC motor, specifically the DC separately excited DC motor, the flux and the torque producing eddy currents are orthogonal and can be controlled independently. And we know that here the torque being produced by separately excited DC motor is given by this expression where the K is the constant and phi into Ia into If. So if we keep the flux constant, or let's say the field current constant, then just by controlling the armature current, I can control the torque. Similarly, I can also control the torque through my field flux also. So the same thing, because here in the DC separately excited motor, the flux component and the armature component both are decoupled. However, in the AC motors, the flux component and the torque component, these two components are not decoupled. So what happens that FOC is the technique which is used to achieve the decoupling or the decoupled control of the torque and the flux by transforming the stator current quantities from stationary reference frame to torque and the flux producing current component in rotating reference frame. And this is being done through the Clarke's transformation and then subsequent to it the Parkes transformation. So here to transform or for the decoupling of the stator current, the phases are, let's understand that this is the my stator current, which is 120 degree placed electrically. So all these three phases are 120 degree apart from each other, and this is being converted into the two-phase quantity or the two-phase component over here, which is the alpha and beta. So we will get the two current values at I alpha and I beta, and these two current are orthogonal to each other. So that means that these two components are 90 degree apart from each other, and this is being done through the Clarke's transformation. So the three-phase waveform is being converted into two orthogonal component, or the two phases which is being placed orthogonally with each other. So they are 90 degree. This is 90 degree, and the further to this is being converted into the two axes. One is the direct axis component, the other one is the quadrature axis component. So here it is being shown that this is the direct axis component and this is the quadrature axis component. So direct axis component, I can say that which is being placed along with my pole. So let's say if this is my pole, so direct axis will be along with my pole itself. And whereas the quadrature axis component is 90 degree to my direct axis. So here rotor reference frame DQ, here this is nothing but the D and Q. So the rotor reference frame DQ, in which the axis is along with the NS pole or along the flux vector of the rotor, and the Q axis is at the 90 degree of the to the D axis. So here we have the combined representation of all three frames. So first is this stator stationary reference frame, which is here. The three currents are shown as IA, IB and IC, and all these three components are 120 degree apart from each other. So this is 120 degree. Whereas the alpha is in phase with the IA itself. So here that's why the I alpha is in the phase with the IA itself, and I beta is 90° or orthogonal to my alpha axis. And then we have the direct axis converted from the alpha beta. We have converted this into the direct axis and the quadrature axis through Parkes transformation. And here the direct axis is a kind of a arbitrary rotating frame of the rotor, so which is converted from the reference stationary frame to arbitrary rotor frame. And this direct axis in the along with the poles, and then quadrature axis, again the angle between direct axis and quadrature axis is again it is 90°. So this is the combined presentation of all the three frames. And to do so, we have to do the forward transformation. In the FOC, we have to do the two transformation. One is the forward transformation, where we convert the stator currents into the rotary frame. So taking feedback from the rotor position and then converting into the from three-phase to two-phase orthogonally placed, and then from two-phase to something like which is my in the DC component value in the direct axis and the quadrature axis. So this through this here we have the decoupling over here. So decoupling is being done through the two transformation. In forward transformation, which is happens through the Clarke's and the Parkes transformation. And here the decoupling, after the decoupling, we can control the torque and the flux independently. Here the direct axis is responsible to control the flux, whereas the quadrature axis is responsible to control the torque. So by these two, I can control the flux and the torque independently, just like I can do it in the case of the DC separately excited DC motor. So here in this video, we are going to focus on the Clarke's transformation. We will see its derivation in the forward and in the reverse also. So this we are going to. So first let's understand that why we are doing the forward transformation. So forward transformation is being done to control the flux and the torque independently through the PI controller. So because the PI controller can easily work on my DC values, so I can use the PI controller for flux and the torque separately. Once it generates my control signal, then it has to be fetched to my inverter, which can control my further motor speed and the motor torque. So to do that, after the PI controller, we have to do the reverse transformation. So in the reverse transformation, first Q and D axis need to be converted back into alpha beta frame, and then from alpha beta frame we need to convert back into the three-phase value. So I hope we have understand that why we have given this name the forward transformation and the reverse transformation. So in the reverse, it is known as the inverse Parkes transformation, and similarly here it is known as the inverse Clarke's transformation. So in this video, we will see the derivation for the transformation matrix, Clarke's transformation matrix in the forward and in the reverse, both. So the transformation of stationary circuit to a stationary reference frame was developed by the Edith Clarke. And the Edith Clarke was an American electrical engineer, and she was the first woman to be professionally employed as an electrical engineer in the United States, and the first female professor of electrical engineering in the country. So she has given this transformation, and it is very beautifully presented. For the forward transformation, the matrix is here. A matrix to convert the alpha beta frame through the three-phase ABC reference frame. The transformation matrix, which is shown over here by T, is given by this matrix. where IA, IB and IC, these are the three-phase currents of the stator. And here the gamma is nothing but a zero sequence component. We will see that why zero sequence component has been considered here, because we only required alpha and beta. So why here the zero sequence component is being included? So we'll discuss this while doing the derivation. Similarly, for the inverse Clarke's transformation, we have this matrix that it is being converted into again the three-phase frame ABC from the two-phase. Here again it is, instead of gamma alpha beta, it is also has the gamma, which is again the zero sequence component. So to see the beauty of this, first we need to understand that how we are going to do this IABC need to be calculated through this transformation. So very obviously, by looking at this relation, we can convert this just by transpose of this transformation matrix or inverse of this transformation matrix and into I alpha beta gamma matrix. All right. So here, this inverse, which is the, we need to take the inverse of this matrix over here, is nothing but the transpose of this matrix. So here it has been done so beautifully that if we have to take the inverse while doing the reverse transformation, it comes out to be the transpose of this transformation matrix. So here, if we'll just look at this, the conversion from here to here, it is nothing but it is the transpose of this matrix. So we need to understand it, that how it is happening. So let's begin with the derivation for it. To begin with the derivation of the Clarke's transformation matrix, let me start it with the phasor diagram. So first I'm drawing the three-phase values over here. So stator current three-phase value. So instead of only current, I'm taking this as phase values A, B and C. Alright, and as we know that alpha is, let me draw the alpha over here. Alpha is in phase with the my A phase. So this is, let's say here, this is alpha, and we know that beta is orthogonally placed with the alpha, so it is something like 90 degree. So this is my beta. All right, so now we can begin with the derivation of it. So let's have, instead of only current, I'm taking one vector over here. Let's this is F, and this vector F, it can be anything. It can be vector for current, it can be voltage, it can be flux linkage, it can be charge also. So as we have seen previously that we have seen the matrix in the terms of the current. So let's have this vector as here F, and representing this vector F in terms of the A, B, C phases will be equals to FA vector of this value, which is over here, FA vector of FA, A cap, then FB, B cap, and then FC and C cap. And vector F in terms of alpha beta phase, it will be F alpha, alpha cap, and F beta and beta cap. Here F alpha is equals to, it is nothing but vector F dot alpha cap. So we have this. So from here we can find out the f alpha is equals to, let's put this equation over here. So we have fa a cap, this is a cap, plus fb b cap plus fc and c cap into dot alpha cap. So just by opening this expression, we will have the fa a cap dot alpha cap plus fb b cap dot alpha cap plus fc c cap dot alpha cap. So solving this expression further, this is a cap into alpha cap is nothing but the angle between a phase and the alpha phase. So we know that, and cosine of it. So we know that the a and alpha, they both are in phase. So this is nothing but fa into cos of 0 degree plus fb, the angle between B phase, which is here, and the alpha, which is here. So we know that the alpha is in phase with the A. So the angle between A and B is nothing but 120 degrees. So similarly, between B and alpha is also 120. So cos 120 degree, and plus similarly here we have the FC, the angle between C vector here and the alpha. So we know that the between alpha and beta we have 120, and B and C is 240. So we can say that it is cos of 240. All right. So putting the value of these, this becomes cos 0 is nothing but 1. So this is FA plus FB cos 120 is the 1 by 2 minus 1 by 2. So this becomes minus of 1 by 2 FB, and this becomes cos 240 is plus 1 by 2. So this becomes 1 by 2 FC. So here we get our the first case, which is the expression for this is nothing but f into alpha. Similarly, finding for f beta, so f beta will be similarly the vector f dot beta cap. Putting the value of vector f over here, so f beta will become equals to this again fa a cap plus fb b cap plus fc and c cap dot beta cap. So expanding the expression, we will get it the fa a cap dot beta cap plus fb b cap dot beta cap, and similarly we have fc c cap dot beta cap. So again finding the value of between these two, so we will have the cosine angle between a cap and a and beta. So we know that this is my a phase, this is b, and this is c, and the angle between a and beta, because alpha is in phase with the a, so it's nothing but the 90 degree. So this will be fa cos 90 degree. Similarly fb, the angle between b phase and the beta, so this angle we are talking about. So between a and b the angle is 120, and alpha and beta is here 90 degrees, so this angle becomes 30 degree. So this will become of cos 30 degree. And similarly we have fc, and between c and beta this is 30 degree already, between B and beta, and this angle is 120. So this total becomes 150. So cos 150. And this is further, this becomes 0. This becomes cos 30 is nothing but the root 3 by 2 FP, and cos 150 is nothing but the root minus of root 3 by 2 FC. So we have find out beta F beta also. So similarly to the F alpha. So as per this, now I can say the matrix for F alpha and F beta. Again, please remember that here the F we can have anything like current, voltage, or flux linkage. So this is we can understand as a matrix of current or as a matrix of the voltage also. So it will become equals to 1 minus 1 by 2 minus 1 by 2. And similarly here this becomes 0. This becomes root 3 by 2 and minus of root 3 by 2. This is plus 1 by 2. And into we have FA, FB, and FC. So we have got the matrix for alpha and beta values over here in the frame of alpha beta frame from the three-phase stator reference frame. However, if we have to perform the reverse transformation, I mean the inverse Clarke's transformation, so it is not going to possible because this matrix is not a square matrix. So this does not allow the reverse transformation of the Clarke's matrix. So therefore, the class has considered, the edit class has considered one more component instead of the alpha beta, which is they have taken as a gamma, which is known as the zero sequence. And the edit class had also considered that this zero sequence will not have any impact or will not have any effect on the alpha beta frame, because it has considered that the system is balanced system, and for the balanced system, for the current and the voltage, this expression holds true that IB plus IC plus IB plus IA plus IC is equals to 0. So therefore, the zero sequence will also have the 0 value if the system is balanced. So this assumption was a very beautifully taken for this transformation by the edit class. So let's understand that how this zero sequence is added and then how it can be converted into the reverse transformation. To do so, now we are taking that zero sequence, which is, let's say, F gamma I'm taking, here is equals to FA plus FB plus FC into, let's say, some constant K, and is equals to 0. So putting this into matrix form, now our matrix gets changed something like this: F alpha, F beta, and F gamma, which is the zero sequence, and that is equals to some constant I'm taking over here, let's say K1. Why? Because I'm taking this constant to have the flexibility while doing the reverse transformation or to taking the inverse of my matrix. So it is 1, it is minus 1 by 2, and it is plus 1 by 2. This becomes 0, root 3 by 2, and minus of root 3 by 2. And last, this will become K, K, and K for the zero sequence, and into we have FA, FB, and FC. So we have taken the two constant over here, constant K and constant K1. So let's find out the value of these two constants. To find out the value, why we have done this? Because it was not possible to take the reverse transformation. So let's take the inverse of this matrix. So taking the inverse of this matrix, I can represent the value of FA, FB, and FC in terms of the alpha, beta, and gamma. And the matrix comes over here that 1 by K1 into 2 by 3. And the matrix is 1, 0, 1 by 2K. Similarly, minus 1 by 2, root 3 by 2. And this is 1 by 2K. And 1 minus 1 by 2 minus of root 3 by 2. So this will become, this will become plus, and minus root 3 by 2, and this is minus of 1 by 2K, and into F alpha, F beta, and F of gamma. So now here, as we have talked earlier in this video, that it was a beauty to this transformation matrix I'm showing as a T. So taking the inverse of this transformation matrix comes out to be the transpose of this matrix, because it gets easier for the computational purpose while using the microcontrollers to implement the FOC for the control of the real motor. So it becomes easy to have such matrix which gives the inverse is equals to the transpose of it. So therefore, we have taken this flexibility while doing the reverse transformation, or while doing the while taking the inverse of this matrix, so that we have assumed these two constants K and K1. So now here, looking at this K over here, if I take the, and I just want to have the transpose of this matrix, so very obviously the value of K is nothing but 1 by root 2. So putting 1 by root 2 over here, I will get this column will get replaced with the value of 1 by root 2, 1 by root 2, and 1 by root 2. And here this row will be also 1 by, so here taking the value of 1 by root 2, this will become 1 by root 2 instead of K. This also will become 1 by root 2 instead of K. And this will also become 1 by root 2 instead of K. And here this column, this value will become nothing but 1 by root 2. This will also become again 1 by root 2, and similarly the third will also become 1 by root 2. So now this matrix becomes the transpose of this matrix. So the inverse is nothing but the transpose. And here the K1 value, if I'll just take the K1 value here, is equals to root 2 by 3. So here putting the value of root 2 by 3 constant here, and this value will also become the whole value will also become is nothing but the root 2 by 3 over here. So exactly the whole matrix, taking the inverse of this whole matrix, will become nothing but the transpose. So therefore it becomes very easy while doing the inverse Clarke's transformation. So I hope we have understood that how the Clarke's transformation is being done and its derivation, and why the zero sequence component is being taken into consideration. In the next video, we will take the Parkes transformation, and we'll see that how this alpha beta frame is being converted further into the two DC components, which is the direct axis and the quadrature axis, which gives the better control of my motor by decoupling the torque and the flux. Thank you.